and you can tell any issues behind that after all.
Sir, is it
Hmm?
possible to have it in the evening so we'll have time to revise in the morning?
Okay, so Saturday evening,
Sir,
5 o'clock.
evening is not possible, sir. We've made other commitments because it's weekend.
Okay, then I will conduct on Friday evening. Is that okay? Or evenings are okay. So Saturday morning, 10 o'clock is fine, I think. Anyway, you can tell about your opinion upon that. If it is very important, by then I will consider that. But anyhow, it's supposed to be conducted within this week because I have to evaluate and post the marks. Well, we will go into the topic, and so you can listen the class carefully. Whenever you have issues, you just we can immediately uh, talk and you can ask about that. So then,
Excuse me, sir.
mhm,
Sir, sorry to interrupt, but one small request. Like,
mm,
could you give us an uploading option for like a single file where we'll like write all the answers and upload it as a single file? Because uploading a
yes,
separate file takes a lot of time. So,
sure, sure, sure. Yes, yes.
okay, sir.
Yeah.
Thank you.
Okay. So we have completed the electrostatics, and we are now in magnetostatics. So magnetostatics is equally interesting as electrostatics. So you have to self-estimate that how far it is interesting. So somebody who likes physics, uh, like so they definitely will like these two topics as well. Means all electromagnetic theory very well. So engineering is nothing but applied physics. So obviously, if you all people volunteer into this course means most probably people will like it. So if you have problem, you can just message me through Teams, and I will think over that, and I can make it the problem simpler. Okay. So, so in case of magnetostatic, it is actually a very smaller unit while comparing the first unit. You have hardly two important laws, and the third one is the magnetic flux, so which is very similar to that of the electric flux. So if you understand these two laws, then very well you can solve almost all the problems in the magnetostatics. And in case of CAT 2, so these two modules will come, and I have highlighted what are the modules will come. So the black color ones may not be coming. Okay, so these concepts supposed to be studied with time varying principles. Then only we can. So I will come these means I will take these topics when we study the time varying ones. So now, as of now, time invariant electrostatics and magnetostatics will be coming for exam. So this CAT 1 syllabus will note down this, and almost all the slides are uploaded. If you have any issues, then I will give much more in detail in future. So I will be taking a few numerical problems as well. So that also I will upload it. Okay. So we already learned about the basics of the magnetic field concepts. It is evolved very long back itself. In fact, the very first one has come was magnetostatics. Then the electrostatic theories were evolved. So, but anyhow, the theoretical representations were evolved with electrostatics first in the time of Lord Kelvin as well as Coulomb's time. So these theory were being evolved. Then they later analyzed the magnetism and they have come up with that idea. And almost from you can see several theories were being evolved from 1760s to 1830s around that. So in these times only some of the very important laws, including Ampere's law, Biot-Savart law, and then other even the Gauss law, and even some of the important Maxwell's equations also derived upon this particular time only. So this particular time is very important for the electrostatics and magnetostatics. And after this, 1940, Maxwell has already published papers on this time varying concepts. and thereafter time varying concepts were being evolved. One of the important applications of the time varying one is antenna. So after the evolution of the antenna, we got wireless system all the way. So this all theories you're supposed to know about that. So in case of magnetostatics, it is originally established by this Oersted, and he actually worked in the lab for nearly about 13 years, and he found the ideas of the magnetic field, how it is being produced. So he told it is this magnetic field can be produced only by the charges which are going in a particular velocity, which we call as a current. And this also same thing applicable to spinning electron, which is having angular velocity. So this the atomic currents which actually produce the magnetic field, and these all spinning electrons of each atom altogether will start combine, which in other words we call as a linkage, and that linkage makes the magnetic field just going from one pole to another pole, okay, in a loop manner. That is the main difference between the electric and magnetic field. So the electric field will be excited out of the structure, and just perpendicular to that you will be having magnetic field. So this actually, upon the notes of Oersted, Bayes-Savart law being derived. So this clearly indicate the principle of the electromagnetic field due to the current flowing in a particular system. So here it is, there is a wire is taken or a line. So, and in this line, there is a current I is passing, and therefore the magnetic field will be going exactly inward to its because the current is going in the upward direction. If it is going in the downward direction, the magnetic field will be just going in this direction. So it's supposed to be marked by this dot and this. And so here we have the scalar form and vector form. So is you supposed to remember only the vector form. Scalar form will vary with respect to the orientation and the other important aspects, particularly the normal vector what we draw. You always remember the vectorial form. So it clearly indicate that if there is a current which is passing, and that current is a vectorial representation, and the point at which we supposed to calculate the magnetic field, if we draw a line and which simply make the vertical connection, and this two product actually when we take it, then this will give us the unit vector of the magnetic field, and this is actually given with the ratio of 4 pi r square. So this is how we can easily write the magnetic field vector. So that is what it is described here. And since two vectors are coming into the picture, we're supposed to take the cross product of that. And because the resulting vector will be in the perpendicular direction to both. So in order to describe that, the cross product often will be taken. So here the current IDL will be called as small current element, and this R vector is the line vector which is joining the current carrying conductor and the point P. So, and this denominator you can see 4 pi r cube. This r cube has come because r square into another r will come. So that is the overall representation of Bayes-Savart law. And Bayes-Savart law can solve most of the magnetic field problems. So this again, in order to remember the Bayes-Savart law, you can use this simple principle. So this actually I even use in my regular calculations. I always pick up right hand and put a thumb, and I will think in which direction it goes and up and down like that. So you can also very well use this scheme. And other things you're supposed to remember in this magnetostatics is the current. In various form, the current will be available, as it is very similar to that of the different charge densities in the yeah, electrostatics. Here we have different current distributions. So one is actually line current, another one is surface current, and the volume current. So which are described. Often this is supposed to be named as current densities. So I is current density, and K is current density for a surface distribution. And then V volumetric is meant for the current actually flowing in the volumetric structures. And the corresponding integrations is also given over here. So you're supposed to be very careful about that. Here, this dl is the vector and these two are vectors. And in case of here, the current will be the vector. And this. So these are the some of the key important points you're supposed to. So when you work out in the electrostatics as well as magnetostatics, the very important thing you're supposed to remember is the vector. So by practice, you will easily identify which is vector, which is a scalar, and the product in what way it will come and how to define that, and dot product how it will come and cross product how it will come. So you can always see it means you're supposed to practice in that way. So this we already have seen the derivation that for a straight current wire, which is having width almost 0. So we can say it is a line current. So when a current is passing in a particular line starting from A to B, then what is the magnetic field at a particular point B? So in order to do that, we have taken the line along the Z axis, and this line is located at a particular point from the origin point. So with respect to, let's say this is X, so this let it be, this is X axis and Y axis and the Z axis. And in that case, we can easily represent in terms of the cylindrical coordinate system. So here the cylinder you can draw. So then you can define the points like rho, comma, 0, comma 0, okay, along the x-axis. So similarly here, the points, this particular point you can represent as, since it is about h 0, comma 0, comma h. So the very first thing you have to find in most of the cases in the Bayes-Savart law is you're supposed to define this ideal and this R vector. So you can first you have to calculate these two, and remaining things you can easily substitute by means of taking the magnitude of that. So it is very, very easy. First you have to find DL vector and this R vector. Just you have to take the cross product of them. You will get this vector. Then you have to just integrate that. It's very, very easy procedure to get out of the Bayes-Savart law. And here we got the expression for a finite wire, which is carrying a current of I and at a distant point rho, and with the angle of alpha 1 and alpha 2 with respect to the edges of the line, then what is the magnetic field? So this length increases, this alpha 1 and alpha 2 will vary, and this difference will give us the difference in the magnitude as well, and the location of the point P, and that also can vary subsequently. By the way, this if we take this wire and at this particular point along the Z axis itself, if you notice that along this particular direction, if it is available, both alpha 1 and alpha 2 will become 0, then you will get totally 0. So in other words, we can say that magnetic field will not be available because the magnetic field will be just always will be around this. And at this particular point, it may not be. So it will be very, means is supposed to take this concepts in a particular visual basis, so that you can understand the magnetic field, how it is distributed around the structure. In this particular problem we have seen, so I have done everything with my handwriting, so for many of you might be it is confusing. So I have simply taken from Sadiq's solution. So first actually you can see that Sadiq described the problem, because in the exam or in the real time, the structure, nobody will not draw it. So only you will get this problem, and this is actually given. So only this two alone given, and the with respect to the side one, we have to calculate. It is along the x-axis. So you can redraw the structure in your own way. So for example, I have drawn in this way, which is a 3-dimensional space. And if you feel it is confusing, you can very well use it this way. Okay, so you can also put this y-axis in this direction or in this direction, whatever the direction you like. So here, anyway, the problem here is along the along the z-axis, and the rho is along the x-axis. And here the rho is along the z-axis, and just it is simply interchanged. So there is no change of any principal in by any means. So you can directly use the expression directly. So just first you have to calculate the cos alpha 1 and cos alpha 2. So both you have to calculate, and then you have to substitute the value for rho, and you will mostly get the answer because it is a very straightforward formula. But the interesting or the very important part in this case is the direction of the magnetic field. Okay, so at this particular point P, so when we calculate with respect to this, we can easily draw. I used to draw like this. So this is the thumb, and we have the fingers. So the magnetic field will be just like this. So this magnetic field will go in this way and will cross this way. So here the magnetic field will be like this. The magnetic field will be going in this particular direction. Now the question is in what direction it will be available. So it's supposed to be perpendicular with respect to z-axis as well as along the x-axis. So it must be y-axis, but since the current is going in the perpendicular, so obviously it will go in this opposite direction. So if we define this y direction in this axis, then obviously it is minus y direction. So in other words, we can easily take the cross product of them. So I believe you know how to do the cross product. This ax vector, ay vector, az vector, and then you can substitute the values of them. So, but here it is given with this cylindrical one. So phi and z, and then here you can put the other values. So this ax vector is going to be telling about, so this is ax vector, and this is actually 0, 0, and then along the z-axis we have ay vector. So this value is 1, and this value is 1, and 0, 0. So when we do that with respect to a5, then you will get 1, 1, 0, 0. Okay. So whether it is correct or not. Okay, so very first one is along the, okay. See, along the z-axis, now we have this ax vector. Along the z-axis, we have this. So this is supposed to be 0, this is supposed to be 1. This is supposed to be 1, this is supposed to be 0, like that. So when you put that, you will get minus 4. That is why you got like this. Okay. So in order to avoid these all confusions, you can draw this thumb and other fingers when you draw. Then you can easily find out that in what direction this magnetic field will be available. It is very, very easy one. The same principle you can apply for other cases. So you can apply here, and you will see that the magnetic field will go around that. So the magnetic field will be available both with respect to x and y axis. So that is what the answer will be. And the same problem we can extend for many structures, many loop structures. And here is one example for a circular loop. Okay. So there is a circular loop, and the circular loop is defined with this. And so in this, can anyone say what is the radius of the circle?
3.
Yeah, great. So for the circle equation is x square plus y square plus equal to r square. So this is the circle equation. So in that radius, so therefore radius will be 3, and this is actually located on z equal to 0 axis, which means along the xy axis it is located, and it is carrying a current of 10 amps and along the phi direction. So along the phi direction it is going on. And now we have to calculate the magnetic field at these 2 points. So just which means from here and here, like that, 2 different points. So instead of directly applying the workout, it is very difficult to work with this directly with the numerical cases. But if we derive the expression for the magnetic field at for arbitrary radius and arbitrary location, then we can substitute the value later on, and the problem become very simple. So how to do that? So first we have to draw the current carrying conductor, which is a circular loop. So which is having a radius rho, and which is actually along the z equal to 0 axis, 0 plane. Okay, and just above that, exactly just above the origin at a particular height along the z axis, we have the point P. At this particular point P, we have to calculate the magnetic field. So that is what our objective. So the answer is very simple. It is very same as that of how we have done here. So whenever you have the structure, you have to take a small portion, and with respect to the small portion, you have to calculate this dH. So this dH is made up of two things. One is this IDL, which is a vector. Another one is the line joining vector. So when you take the cross product of them, you will get the dH. Then you have to integrate over the given point. Okay, with respect to, for example, if you here it is integrated with respect to line, but in case of the circular one, you have to integrate over the closed loop path. So it is very simple. So first we have to say what is the electric magnetic field. So the magnetic field is simply nothing but current into the line joining vector, the cross product of that, and the denominator you have this. So as I previously told, you have to calculate this IDL and this R vector. So simply DL and R vector, if you calculate, it is more than sufficient. So here it is clearly written what is this DL. Okay, so how to define this DL? If you take a small length over this, so this small change is nothing but d phi, and you have to multiply with this rho. That's all. So that is nothing but rho d phi, and the vector, that is a phi vector, is directly coming, and we have to calculate the line joining vector. So this particular point, in terms of cylindrical coordinate system, we can say it is nothing but rho comma 0 comma 0, let's say, and this one 0 comma 0 comma h. Okay. So then we can move this point later with respect to phi. That's not an issue. So now we have to find the difference. Always end point minus starting point. So end point is h, and the starting point is rho is coming. So supposed to subtract properly. So 0 minus rho, you will get minus rho, a rho vector, h minus 0 plus h, so z vector. In between, phi vector is not available. Okay. So you can very well see most of the cases, this R vector will be complementary to the L vector, because both supposed to be orthogonal to each other. Okay. So it is very simple. So now we have to take the cross product of that. So first you are placing the unit vectors, then you are going to place the first vector, that is the DL vector, then R vector is the second one. So by placing these two, you got it. Then you have to find the determinant of that. So you can easily do that for, so first you have to work out for this calculation. So you will get rho h and a rho vector will come. And when you do for this a phi vector, you will get 0. And similarly, when you do for z vector, you have to do this. So this multiplication is plus, this multiplication is minus. So minus and minus will become plus rho square d phi. And this is az vector. So, so this is the cross product, and this cross product you are going to substitute over here. So you can very well define the dH vector. That is the small magnetic field induced by the small current element dl or IDL. So here you have the cross product. Here you have 4 pi r cube. So this is r cube, and that is actually has two components. One is along the rho, along the z components. There are two components available, and now this is completely a symmetric structure. So what is meant by symmetric structure? Can anyone say that? So a square, can it be a symmetric structure? So when you draw a line, symmetric or the line of symmetry, then it can exactly divide into two. So the same way we can put it here. And interestingly, for circle, it can be the axis can be in any this line of symmetry we can draw anywhere else, just that it go diagonal. That's it. So that is called circular symmetry. And using this circular symmetry, we can clearly see that. So if you draw a line of symmetry and you will be having one dl vector and corresponding you will be having one dh uh, z vector, which is we can mention as one, and corresponding dh rho vector. And similarly, this is actually going in this direction. So we can say that this is the thumb and we have the fingers here. So magnetic field will be just in this direction. So it will go like this. But in case of here, it is exactly opposite. So we have the thumb here and fingers here. So you will get the magnetic field in this particular direction. So which means this vector. So both these vector at this particular point P, they will be exactly 180-degree opposite. So they will cancel each other. So you will get only this vector alone. So this DH vector, DHZ vector alone will be surviving. And what about this rho vector? They will be simply cancelling. So even if you do the integration, obviously due to the circular symmetry, you will get this. This particular vector will be cancelled. Only you will get Z component alone. So that is what you have to integrate along. And so when you integrate over that, so here we are going to take rho square. So rho square d phi. And if you see that there is no phi component anywhere for the integration purpose, so we can take all other things outside. Only d phi component is going to be there. That is going to give 2 pi. So this 2 pi and 4 pi you can cancel and you will get the magnetic field due to this circular loop along this axis, along this z axis. So H can be anywhere else. So you can substitute simply H value anywhere else, and it may be positive, negative value. Definitely it works well. So since the square is coming for positive or negative value, it is going to give the same magnitude. That there is no positive, negative here. And for rho, it cannot be for a negative value. There is only positive values will be available. Okay. So by the way, you will get the magnetic field most probably you will get as a positive value, at least along the z-axis, which means the magnetic field will be always in this direction. So you take any particular point, it will go in the same direction only it will go. So that magnitude, when you substitute the current I and rho value 3 and H 4, it can be plus or minus 4. So you will get the same answer of this will come. And so by changing the current and the loop radius, you can also control the magnetic field. So this is a very, very simple solution. And you can also think about calculating for a square. Okay, so just to plan it, maybe such a question may come in the exam. So think of and how we can use this particular principle of taking a loop. So this is how the magnetic field will be available for a circular loop, which is carrying a current I. And here, so this is the point. This is the z-axis. Okay, so along that at any particular H, if you take, you will get the same vector along this particular direction. But the moment you move the point P in the outward direction, you can see that it will be that other component, this rho component also will be coming into the picture. And at this particular case, only rho component alone will be available. Magnetic, this two component actually will not be available at all. So that is a very interesting part, and you will get this interesting pattern of magnetic field just around the loop. Okay, and if you do for two cases, you have one loop, just another loop. If you calculate, at least with respect to this axis, you always know that this magnetic field will be always be perpendicular. And this, so due to, let's say, this particular point, at this particular point, we can say magnetic field due to this first loop and second loop, we can simply add each other. So, and this is how that they are following the same axis and follow and give us the linkage between these two magnetic fields because of the two loops. And more easily we can do like this. We can take like this and another loop and like this, another loop like that actually. So this often referred as helix. So by means of placing a helical wire strip and giving some current source here, then you can definitely get such a very high strong magnetic field, and that will be acting like a magnet. So when you place some magnetic material, the advantage of the magnetic material is it can retain the magnetic field. So if you place the iron rod and give this current for about, let's say, 2 minutes, and all the atoms will be polarized into this particular direction, and it will become a magnet. After some time, it will change its orientation when the saturation fails, which means it will become demagnetized. Then again we can, so that become electromagnet. So that is the principle of it. The same principle you can apply in multiple places. For example, this is the magnetic field of the Earth. This is actually calculated originally by multiple satellites which are roaming around at the outer orbits. So this distance will come around some 30,000 kilometer. So this 30,000 kilometer, it is not still space. Okay, I think after 1 kilometer only, you'll get the space. The moon is still very far away from there. Okay, so and we can clearly see that this z vector is not available. Okay, so the z vector component is missing. So this is giving us the solution that how this internal magnetic field will be. So internal the magnetic source will be available. It might be available a lump, not necessarily like a spring-like structure might not be available. And within this space, the other particles, alpha and other particles will come and hit the atmosphere, and we will get this aurora here. So that is what this this I think you could have seen in some of the videos. You could have seen this. So this aurora is actually coming out of this. So magnetic field is also acting like a shielding for us. So far now we have discussed everything in terms of the Biot-Savart law. So Biot-Savart law is very powerful one, and it can solve many critical structures. Even for some of the very symmetric structures, it can easily give the answers out of it. And very similar to this period, that is in 1920, 1820 itself. 1820 is supposed to remember three things. This This actually, Oersted actually he has given the, I think, fourth paper on magnetism, and he clearly described how this, and the same year, Biot-Savart law being derived. At the same time, actually, we got the Ampere's law. So three people, we could say that Ampere is very great in terms of his theories in the electricity, and I think he has given the ideas to in his through his publications, and largely influenced by uh, Kirchhoff. So Kirchhoff actually he has learned many things from the notes of Ampere, because I think both are from the same region, France only. So this is the year actually we can say that year of miracle in terms of electromagnetics. So this year only Ampere's law were being derived, and instead of directly taking the current from current with magnetic field, so this is actually reversely written. So this very much look like that of actually Gauss divergence theorem for a closed surface. So here it is for a closed line. So what actually Ampere's law states that actually, so if you can do the line integration of magnetic field just around the current carrying path, then you can easily calculate the current out of that. So in other words, you can say that, so if there is a wire is actually going in this direction, and you just draw a closed path. Okay, this closed path actually often referred as Amperean path. So I just say that is a Amperean path. So this Amperean path, we can put a dl vector. So this, if you integrate over this closed path, so this closed path integration for a dl, then you can calculate the magnetic field out of that. So this is the magnetic field. We are going to take the dot product. You will get the magnitude, the scalar one, and that you integrate, you will get the total current I. So that is what the, so this is a kind of grouping all the field lines due to this, means the field, all the magnetic lines, which will give the, so it is very, very same as that of how this flux density and the charge density is linked. So the same here, it is how the magnetic field and the current both are given over here. Actually, so this, after writing that, at that time, Lord Kelvin already reported about this uh, the cross product of both this del operator as well as the vectors. So he simply applied that. I think about 10 years before, to him only, Lord Kelvin has derived the expression for this del cross a vector. Okay, so del cross, so any particular x vector or something. So when you do, what will happen? So this actually very well be noticed, and I think Ampere also he studied in his times in the in his, I think he was around some 17 or 18 when he was writing this particular theorem. So he is so young than you on this particular period actually. So in your time, actually Ampere is almost like he is legend in his field. Okay. So if you notice that most of the people, most of the Nobel laureates, their contributions before the age of 25 only has given them. The only exceptional person is Mary Curie. So she did after 30. So, but all other people, in my knowledge, they have accomplished their some of the very noble work before 20s, 25. So your age is actually very close to that, is it? 20 to 25. So this is your crucial time. If you put your effort, if you, so you can become legend. Well, so we got the, so we can apply the Stokes theorem. So what Stokes theorem says that if you want to, take the, just imagine this is a particular vector, and this vector you have to for a closed path. If you want to take the integration, then you can easily do it with the curl of that. So just to take the curl of the particular vector and take the dot product with the surface vector and just integrate over the surface. Whichever is easy to you, you can do that. If you feel that this is very easy to me, then you can work out on that. But for some of the critical cases, loops, this integration might be difficult. So in that case, you can easily do for a surface. So you can take this, this is a closed path. This closed path has its own surface. So if you take a small surface, just perpendicular to that, you just take the ds vector. And this ds vector, you have to integrate with respect to this curl of that. So then you will get same current will come. And it is very well known that the current over the closed path can be simply nothing but the integration of current density. And by comparing these two expressions, one can easily arrive at this del cross H equal to J. So that is often referred as Maxwell's third equation. And but in case of Maxwell's notebook, it was written as the Ampere's law. So this is actually the differential form of Ampere's law. And this one is what you see here is nothing but the integral version of the Ampere's law. So both are, so a big important historical problem simply given in a slide. So this very remarkable one. So this Ampere law is actually very, very useful one. It can solve many tricky problems in magnetostatics. Not only magnetostatics, it is also very useful in the magnetic fields, time varying magnetic fields as well, like motor and all the things actually this will come. And its extended version only is nothing but this Faraday's law, so which tells that automotive force and everything else. So this is why actually Maxwell in his notebook, I think page number 41 or 42, you can see that he has mentioned that is a Ampere is the Newton of electricity. How to calculate for a infinite current using this this Ampere's law. So this is Ampere's law. So it clearly states that you just to draw any closed path just around the conductor such a way that it will collect all the magnetic field. Okay, you should remember all the magnetic field, and then you can easily calculate this. How accurately you are collecting all the magnetic field, that accurately you can calculate the current. For instance, when you use this type of path, this type of random shaped path, and definitely we will miss out many because it is definitely mathematically very difficult to integrate. So you're supposed to be very careful about this drawing the Amperian path. So in case of Ampere's law application, the drawing Amperian path is the very important. Once you have drawn the Amperian path, around some 70 to 80% this problem is solved. Simply you have to apply the Ampere's law, then you have to integrate it. That's all. Remaining problem is very simple ones. So here we have a infinite line. So this infinite line is carrying a current I, and at particular point from this point P, maybe we can say in terms of cylindrical, it can be 0, comma rho, comma 0, comma 0. So at this particular point, we have to calculate the magnetic field. So how to do that? So it is very simple. As clearly it is noted, the magnetic field and this two supposed to be defined. So what we know is the magnetic field will be just around that according to the simple law. So we can say the magnetic field will be just around the current carrying conductor along the phi direction. So the only component is going to exist is phi component. So we can say that the magnetic field is equal to h phi, that is the magnetic component, and the unit vector a phi, like that. So this is how we are going to define that. The next one is dl vector. So what is this dl vector? The small portion in this Amperian path. The Amperian path is circle at a radius of rho. So we can easily say that it is nothing but rho d phi into a phi vector. So both are a phi vector. Just we have to take the dot product of that. Then you will get h phi into rho into d phi. Okay, so that is what you got here, and you have to integrate over the phi direction. So that is from 0 to along this. So the line path is defined in terms of 0 to 2 pi. So when you integrate over that, you will get h phi, rho, and 2 pi. Then this is nothing but I. So therefore, you can easily calculate that. Therefore, h phi is I divided by 2 pi rho. So this is the pi component. Then you are going to substitute here in this. Then you will get the magnetic field. So that is very, very simple. It is same that expression you got it. Got it here for a infinite case. So this is actually defined in terms of the magnetic, the line integration using the Amperian path. But there is an alternate possibility that if you take the curl and the small surface of the Amperian closed path, then you just do for a surface integration, then you will get the total current. So this also same. So how to do the same problem in that way? So we are going to do this particular integration. Sorry. So this particular. Okay, so we are going to do this part. How to do it? So for this, we need two things: this del cross h and ds vector. So these two things we need. First, we will calculate this del cross h. So this is the formula for curl of the particular vector with respect to the cylindrical coordinate system. So here you can see that first we are defining the magnetic field. The magnetic field is going to be available only along the phi direction, and remaining directions naturally it will be cancelled. So we can say that the term before that also 0 plus 0. Okay, so all these z components, rho components, wherever it is coming, they all going to be 0. Only this phi components, wherever the phi components are there, that alone will be surviving, and that is what we supposed to take it. So that is what it is substituted here. This minus rho d phi a rho, everything is placed. Okay. So now we have to calculate this ds vector. So what is this ds vector? It's a small surface. The small surface is defined with a small d rho and small d phi. So this length, you know that it is nothing but rho d phi. When you multiply that, you will get rho d phi. And the for a surface vector, we will be having the normal vector as the unit vector. So the normal vector is going to be az vector. So that is what it is here. Okay, so now you can see that both are exactly. Just we have to take the dot product. When you take the dot product, you can easily notice that this a5 component will not survive because the dot product of these two perpendicular term will become 0. So only with this z term alone, you will get the term. So that is what we have substituted here. This row and this row will be cancelled. So just you have to integrate this for a surface. So for a surface means in terms of rho and phi we have to integrate. So we have to integrate from 0 to rho and 0 to phi, 0 to 2 pi, and this expression is coming over here. So this particular part, it is a differentiation. When you integrate with that, you will get the internal term what is differentiated. Okay, so that is what we are going to substitute over here. And then we have to integrate over from 0 to 2 pi. So when you 0 to 2 pi, when you do that, this d phi term alone will be integrated. You will get 2 pi here. So rho h phi 2 pi equal to I. So you will get h phi term. So this h phi term you are going to substitute over here. Then you will get the magnetic field. So you will get the same expression. So this you can see that this is a bit lengthy way. So that is why this particular method is very simple. So this is what I already meant, that in case of Stokes theorem or even divergence theorem, whenever you see, so this left hand side or right hand side, you can apply whichever the method you feel very easy, and that actually supposed to be tested. So by experience, you will immediately notice that this is going to be a little tedious. And here you can see that this particular problem look very big actually, but after substitution, the problem become very simple. After another multiplication, we got very simple. So these steps, even though they look big, but by substituting them, many of the term becomes 0, and we will get naturally very simple for them. Then after that, this integration, anybody can easily do that. So this is what I told. First, you have to figure out the problem, and the way you draw the problem also very important. And so you have to go little step by step, the way it's been told. So you just refer the book as well. Okay, so I will teach this rest of the part in the next class. See you then. If you have any questions, you can very well ask me. You may leave now. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.